Hey everybody, welcome back to Complex Analysis. Today we're going to talk more about transformations. And here we say, suppose that A is a region in the XY plane. So here's A, everything inside this loop is A in the XY plane. And suppose that f of z is a complex valued function such that W is equal to f of z, and we can represent it as u of xy, the real part of W, plus I times v of xy, the imaginary part of W. We call f evaluated at A the image of A under F. And what is f evaluated at A? It's all of the complex numbers W in the UV plane such that W is equal to f of z for some z that's in A. So let's put a z1 here in A, and we'll put a z2 here in A. And correspondingly, we'll have a W1 over here and a W2 over here, where W1 is f of z sub 1 and W2 is f of z sub 2. And F maps the element z sub 1 in A to the element W sub 1 in f of A. It maps the element z sub 2 in A to the element W2, or f evaluated at z sub 2 in f of A. And everything inside this loop, f of A, is an element that is equal to f of z for some z in A. Let's look at a few examples just to solidify our understanding of what the word image actually means. Okay, first example. Suppose that A is the positive x-axis. So A is the set of all complex numbers such that x is greater than 0 and y equals 0. And suppose that our function f of z is defined by f of z equals I times z. Then the image of A, f of A, is the set of all complex numbers I times z, or I times x plus iy, such that x is greater than 0 and y equals 0. Well, let's see, if y equals 0, this is going to be 0, right? This term. So what this really is, it's the set of all ix such that x is a positive real number. So that's what the image of A, f of A, is. It's the set of all ix such that x is a positive real number. And let's draw the region A and draw its image f of A. So here's the xy plane. And we said A was the set of all complex numbers z such that x is positive and y is 0. So that's the positive x-axis. That's A. And we take every element on the x-axis and plug it into F. And what it does is it multiplies this element by I. So the image of A is the set of all ix where x is a positive real number. So let's see what that image looks like. Here's U, here's V, and we're looking at all of the, what is this? This is actually the set of all imaginary numbers where the imaginary part is positive, right? So here's f of a. The positive v-axis here is the image of a. A is the positive x-axis, but we take this entire region and we multiply it by I. And what that does is it rotates the region by pi over 2 in the counterclockwise direction. And this is the image of A. So every point on the positive y-axis is such that there's some element on the positive x-axis that gets mapped to it. And this is a pretty easy one to figure out. Let's just pick 3 on the y-axis, okay? So this is the point 3i. What element from the positive x-axis gets mapped to it by the function f? And yeah, I should have I should be showing that f maps this region to that region. Well, let's see. What element gets mapped here? The element 3 on the positive x-axis gets mapped to 3i. Okay. The element 2i here. What element on the x-axis gets mapped to this? 2. F maps the element 2 on the x-axis to the element 2i on the v-axis. So individually, we could say that 2i is the image of 2. We could say that 3i is the image of 3. We could say the positive y-axis is the image of A, the positive x-axis. Let's look at another example. Another example. Here, A is the set of all complex numbers z of the form r e to the I theta, where r is positive and theta is between 0 and pi over 4. So here's the angle pi over 4. And r is positive, so it goes from the origin outward in the first quadrant. If we call this the angle pi over 4, then this ray is going to go in the positive r direction. And this is the set of all complex numbers in here that have positive modulus r. And the angle is between 0 and pi over 4. For example, right here maybe we have 3 e to the I pi over 12, let's say. And maybe here we have 4 e to the 2 pi over 12 or pi over 6, okay, and so forth. Now let's consider what the image of A is under this function f of z. So the image of A, f of A, is the set of all z equals z equals what? R e to the I. Let's see. Let's do it this way. F of z equals z squared. So we'll say that f of A is the set of all z squared, which equals r squared e to the I 2 theta. And since z has to be in this region originally, we'll say such that r is greater than 0 and such that the original angle theta is between 0 and pi over 4. Okay, so this is the image of A, and I think I can do better here. Here's my second attempt. I can say that f of A is the set of all complex numbers z equal r e to the I theta, such that r is greater than 0 and theta is less than or equal to pi over 2. There, how about that? Here is A. Let's look at the image of A in the UV plane. Our angle pi over 4 right here gets changed to pi over 2 by our transformation. So any complex number whose angle theta is between 0 and pi over 2 and whose modulus r is positive is in f of A. So this is the image f of A. And let's see, what happened to this guy? 3 e to the I pi over 12. Well, let's see. The modulus got squared. And the angle got doubled. So this guy gets sent over here to this guy. This is the image of 3 e to the I pi over 12. Now what happened to this thing? Well, the modulus got squared and the angle got doubled, so we're looking at pi over 3 now. So this will be 16 e to the, see, what am I missing here? Can't quite put my finger on it. Oh yeah, this should be 4 e to the I pi over 6. And we square that son of a gun and we get 16 e to the I pi over 3. So the image of this thing, this particular point, under the function f, is this particular point. And the image of the region A, which is this wedge corresponding to the angle pi over 4, the image of A, this slice of pizza right here, is f of A, which is the entire first quadrant in the UV plane. I don't know. I don't know. Okay, here is our first fundamental transformation. We call it a translation. So let A plus BI be some complex number. Then the function W, which equals T of Z, this is T for translation. W equals T of Z, which is defined as Z plus the complex number A plus BI, is called a translation. And here's a picture of that translation. Here's Z, and here's the image of Z, T evaluated at Z. And notice the effect that the translation has on the original point. Essentially, it takes the original point and moves it A units in the positive X direction, and then it moves it B units in the positive Y direction. Physically, graphically, that's the effect that a translation has on a point. And let me write this down the way that I want it to come out. So that's the effect that a translation has on a single point. It takes that single point, Z, and it moves it A units in the positive X direction, B units in the positive Y direction. Now there's something else that we want to notice here, which is important. The effect that the translation has on an entire set of points. And I'll write that remark down right now. 3, 5, 7, 6. Okay. This is probably a helpful observation. The effect of a translation on a pair of distinct points, z1 equals x1 plus I1, and z2 equals x2 plus iy2, is that the images f of z1 and f of z2 of the original 2 points are in the same relative position with respect to one another as were the original 2 points z1 and z2. So, tell you what, I'm going to erase the top part of the board, so I'm going to repeat this again. The images f of z1 and f of z2 of the 2 points z1 and z2 are in the same relative position with respect to each other as were the original 2 points z1 and z2. Now I'm going to erase this just so that I can draw the graph of the transformation. And let's see. All the y values are positive, that's good. Seven. And 6. Okay. Z1 is 2 plus 3i. So here's Z1. Z2 is 6 plus 5i. And now what happens to these points when we translate them? T of Z1 is negative 3 plus 5i. So negative 3 plus 5i. This is T of Z1. And T of Z2, 1 plus 7i. Okay. Now, Z2, which is 6 plus 5i, is 4 units to the right and 2 units above, whoops, sorry for the confusion. This is Z2, forgive me. Z2, which is 6 plus 5i, is 4 units to the right and 2 units above Z1. Now let's take a look at the images of Z1 and Z2. T of Z2 is 4 units to the right and 2 units above T of Z1. So these 2 points have their positions, so to speak, their relative positions with respect to one another, preserved over 4 units to the right, up 2 units, over 4 units to the right, up 2 units. So again, the point of this is that a translation preserves the relative positions of points with respect to one another. If Z1 and Z2 are such that they're 4 units apart horizontally and 2 units apart vertically, then under a translation, their images are going to be 4 units apart horizontally, 2 units above vertically. So their positions relative to one another are preserved. Yeah, cool. Building further on the point, the image of a region A in the xy plane under a translation T of z is the same size and shape as the original region A. So here's the original region. Here's the translation. This is the entire region plugged into the translation T, so to speak. And what we've done is we've taken every point in region A, z equals x plus iy. We've taken every point here and we've translated it by adding a to the real part and adding b to the imaginary part. And graphically, the effect is just that we shift this region over to the right, a units, and up b units. So a translation has this important property. It preserves size and shape. Aha. Yeah, I'll have to apologize to you. Apparently, I had to make you suffer through about 10 minutes of dead air time while I fumbled around drawing the last diagram, and I apologize for that. Now on to bigger and better things. Rotations. The function w equals r of z, and this is r for rotation. The function w equals r of z given by z equals e to the I alpha is called a rotation. And let's see how this works. Let's take any complex number, z equals r e to the I theta, and we'll let r of z be z times e to the I alpha. Then here's what happens when we evaluate the rotation at z. We get z e to the I alpha, but z is r e to the I theta. And when we multiply these two things together, the angles add. And we get r e to the I theta plus alpha. And there are some observations that we want to make. See, here's the image, r of z. Here's the original point, z. And the first observation is that the modulus of z and the modulus of r of z are the same. See, the modulus of z is r. The modulus of r of z is r also. So one of the things that this means is that z and its image r of z are the same distance from the origin. But the point z has been rotated about the origin in the counterclockwise direction by an angle of theta to form the image r of z. Now, I'm going to leave this last statement up. I'm going to erase the rest of the board and draw a picture that illustrates this last point. Okay. Now, something that we remember about a rotation. The image of a point under a rotation remains exactly the same distance away from the origin as the original point. The location of the distance of a point from the origin doesn't change under rotation. But the point z is rotated about the origin in the counterclockwise direction by an angle of alpha to form the image r of z. So here's the original point, z. Here's the image of z, r of z. And notice that both of these points are on the perimeter of the circle of radius r centered at the origin. So z is a distance of r from the origin. Its image r of z is a distance of r from the origin. The only thing that's happened to this point is that it's been rotated about the origin counterclockwise by an angle of alpha. So in summary, the effect of a rotation on a point z, any complex number z, equals r e to the I theta, is that it rotates the point about the origin by an angle of alpha in the counterclockwise direction. The distance of the point from the origin remains the same. Now, is that all that we can say about a rotation? No. We have to address what a rotation does to an entire region. Just exactly how does a rotation affect the size and the shape of a region? And we will talk about that next. Now, we were going to talk about what a rotation does to the size and shape of a region. And the first thing that we do is we figure out that the effect of a rotation on a pair of distinct points, Z1 and Z2, is that the images R of Z1 and R of Z2 of the 2 points are in the same relative position with respect to one another as are the original 2 points Z1 and Z2. And to back that up, first of all, we're going to show that the distance between the 2 points remains the same. The distance between Z1 and Z2 is the modulus of Z2 minus Z1. This is the distance from Z1 to Z2. Now, the distance between the images, R of Z1 and R of Z2, of the 2 points, the distance between the images is the modulus of R of Z2 minus R of Z1. And R of Z2 is Z2 times e to the I theta, e to the I alpha rather, where alpha is the angle of rotation about the origin. And the image of R of Z1 rather, this rotation is Z1 times e to the I alpha. We have a common factor of e to the I alpha. We factor it out. And we have the modulus of a product, Z2 minus Z1 times e to the I theta. So that turns out to be the product of the 2 moduli. And what is the modulus of e to the I alpha? E to the I alpha is the same as cosine alpha plus I sine alpha. And the modulus of this is the real part squared plus the imaginary part squared, cosine squared alpha plus sine squared alpha. That's just 1. So the modulus of Z2 minus Z1 times the modulus of e to the I alpha is just the modulus of Z2 minus Z1 times 1. So where did we start? The modulus, or the distance between the images of the 2 points. And where do we end up? The modulus of Z2 minus Z1. What that tells us is that the distance between the images of the 2 points under rotation is exactly the same as the original distance between the 2 points. So a rotation does not change the distance between points. That's the first thing. Okay, more on the relative position of the 2 points under a rotation. The position of the images of the 2 points, R of Z1 and R of Z2, relative to one another, is the same as the positions of the original 2 points, Z1 and Z2, relative to one another. Now, to start off, we look at Z1 and Z2, and Z1 makes an angle of theta 1 with the positive x-axis. Z2 makes an angle of theta 2 with respect to the positive x-axis. And the angle between them is theta 2 minus theta 1, the difference of these 2 angles. And I guess I should also add something else in here, the distance between the 2 points themselves. And that's the modulus of x2 minus x1. So the distance between Z1 and Z2, the modulus of x2 minus x1. Now let's rotate these things through an angle of alpha and see what happens. Okay, let's take a look and see what's happened to our points under rotation. Under rotation, Z1 winds up here. Under rotation, Z2 winds up here. And what happens? Z1 has been rotated an angle of alpha from here to here. So with respect to the positive x-axis, the image of Z2, please excuse me, the image of Z1 rather, is at an angle of theta 1 plus alpha with respect to the positive x-axis. With respect to the positive x-axis, Z2 has been rotated at an angle of alpha. And so with respect to the positive x-axis, the image of E2 makes an angle of theta 2 plus alpha with respect to the positive x-axis. And what's the difference, or what's the angle here between the image of Z1 and the image of Z2? Well, it's this angle minus this angle. The alphas cancel out, and we just have theta 2 minus theta 1. So the distance between these 2 points, x2 minus x1 modulus, has been preserved. And the angle between the 2 points with respect to these points in the origin, theta 2 minus theta 1, has also been preserved. So the fact of the matter is a rotation preserves size and shape, not just distance, but also position of points relative to one another. So let's draw a picture of just an abstract transformation and see what this looks like. So here's the point. A region A in the complex plane under a rotation has the same size and shape as the original region itself. So the image of a region, R of A, under a rotation, has the same size and shape as the original region. The only difference really is that the region is rotated about the origin, an angle of alpha, and that gives us the image of the region. But the image, same size and shape, just rotated about the origin by an angle of alpha. Now let's see, I guess we have one more transformation to look at. This is, in a way, the last of our transformations, and it's called a magnification. The function W equals m of z, m for magnification, where the function is defined to be k times z, where k is a positive real number, is called a magnification. So if we have z in polar form, z equals r e to the I theta, then m evaluated at z is kz, which turns out to be k r e to the I theta. And what is it that's multiplied by e to the I theta? kr. So k times r is the modulus of m evaluated at z. So a magnification essentially magnifies the distance of a point from the origin. It doesn't change the angle with respect to the positive x-axis at all. So here's z, and let's assume that k is greater than 1, so it really does magnify or make larger. We have z and m of z is going to be this thing. Notice that the angle of z and the angle of the image of z is theta. That doesn't change with a magnification. But the distance from the origin does change. And that's what a magnification does. It alters the distance of a point from the origin. Doesn't change the angle with respect to the positive x-axis. It just changes the distance of the point from the origin. Just to reiterate, the magnification m of z increases the distance of the point z from the origin by a factor of k. So in other words, m of z, the distance of m of z from the origin is k times the distance of z from the origin. A magnification preserves the shape of a region, but not the size. Now here's a remark, and this is important. The transformations rotation, magnification, and translation can be combined by means of function composition in the following manner. We have a translation evaluated at a magnification, evaluated at a rotation, which means we do the rotation first, the magnification second, the translation last. Well, let's see. What does a rotation do to a complex number z? It rotates it about the origin by an angle of, let's say alpha, okay? So this is our rotation. And then we take the rotation and we magnify it. Multiplying everything by the constant k. And then finally, this is the translation. When we combine these transformations by function composition in this order, rotation first, magnification second, translation last, we form what is known as a linear transformation. So a linear transformation is the composition of rotation, magnification, and translation. Let me diagram this just a little bit better than I did down here. This is the entire linear transformation, and this much of it, which is done first, is the rotation. Now, when we take the rotated region and we multiply it by a positive real constant, this is the magnification. And then we take this whole thing, the magnified rotation, and translate it. Okay, it's about time we got to some examples or exercises. Show that the linear transformation, W equals f of z equal iz plus I, maps the right half plane, real part of z greater than 1, onto the upper half plane, imaginary part of w greater than 2. Okay. Here's the half plane real part of z greater than 1. And it consists of all complex numbers whose real part is greater than 1. But the imaginary part can be anything. So the only complex numbers that aren't in this region are the numbers whose real part, x, is less than or equal to 1. So everything to the right of this line, x equal 1, is in the region real part of z greater than 1. And we're told that the image of this region under the transformation is also a half plane. And that half plane would be imaginary part of w greater than 2. So the y part of w, or v, has to be greater than 2. And we'll call this the u-axis, this the v-axis. And this consists of all complex numbers whose imaginary part, v, is greater than 2. We want to show that our transformation maps this region onto that region. And I guess the first thing that I should do is just convince myself that this really is a linear transformation. So f of z is iz plus I. Now, if I multiply by I, that's the same thing as multiplying by cosine plus I sine of something. Where this is the equivalent of I. So cosine would have to be 0 and sine would have to be 1. I guess the angle inside would be pi over 2, right? Yeah, that looks good. And now I can write this in exponential form. This is e to the I pi over 2 z plus I. Oh, and I can see clearly now that this is a linear transformation because this much of it is a rotation. We're rotating z about the origin by an angle of pi over 2. And the rest of it, we're taking this rotated point and we're translating it by 1 unit in the vertical direction. So this is a translation. This is our a plus bi right here, where a is 0. So this is a linear transformation. Just had to make sure. Now, I guess this makes sense. Let me take this step by step and do the rotation first. And I'm going to draw attention to this point right here. This point is 1, 0. And I'm going to draw attention to this point because if I rotate this region by pi over 2, counterclockwise, then this point should wind up here. This point should be rotated counterclockwise by an angle of pi over 2, and the rest of the region is rotated counterclockwise by a distance of pi over 2 also. So we have the rotation this whole region revolved by an angle of pi over 2 about the origin. So now this is the rotated region, and this is u equal 1. This point was rotated pi over 2, so it's still on the circumference of the unit circle. Remember, a rotation does not change the distance of a point from the origin. So this point was on the unit circle, a distance of 1 from the origin, and it was rotated by an angle of pi over 2 counterclockwise. It wound up here. Now we have to do the translation. And what happens there? We add we add 1 to the imaginary part of the real number, or we add 1 to the v coordinate, so to speak. So we don't do anything to the x coordinate, but we increase the y coordinate or the v coordinate by 1. So this point is going to get moved up here. And everything else is going to get moved vertically 1 unit. So here we have the translation. This is 0, 1. This is 0, 2. This whole region just got shifted up by the translation I. So the image of this transformation is indeed the upper half plane. V greater than 2, or imaginary part greater than 2. Now let's see, how did that read? Did it say imaginary part of W? Is that what it was? Yeah. Imaginary part of W greater than 2. That's this region. Yes. Okay, show that the image of the open disk z plus 1 plus I less than 1 under the linear transformation W equals 3 minus 4I times z plus 6 plus 2I is the open disk W plus 1 minus 3I less than 5. Now, I'm not going to be naive this time. I'll look at this thing and I'll say, you know what? This is a complex number. It's equal to R times e to the I alpha for some r and some alpha. And so e to the I alpha rotates z an angle of alpha about the origin, counterclockwise, and then r magnifies this z. And then when we add the number 6 plus 2i, we're translating this. So, yep, this is a linear transformation. And my first impulse is to rewrite everything in this form, because then I can take this disk and rotate it about the origin by an angle of alpha. And then I can magnify it by a factor of r. And then I can translate that whole thing by moving it 6 units in the positive u direction and 2 units in the positive v direction. That's what my first inclination is. So I'll have to change this to e to the I alpha. Let's see, I know what I'll do. Convert to r e to the I alpha. That's what I'm doing. So r equals 3 squared plus minus 4 squared, which equals 5. Well, hey, that looks good. And it sort of supports what we're told. If this really is a disk and I didn't verify it, then it's a disk of radius 1. And if this really is a disk and I didn't verify it, then it has radius 5. So the magnification factor r, 5, jives with what we see. Taking a disk of radius 1 and turning it into a disk of radius 5, this looks good. Okay, now I need to get my alpha. And let's see, 3 minus 4i. So we're in the 4th quadrant. And so I think all we really need is the arctangent of this thing. And, you know what? This isn't one of those things that gives us an angle like pi over 6 or pi over 4 or pi over 3. We don't know what this angle is exactly. With a calculator, we could get close. Ooh, but you know what? We're not going to get exactly a disk with radius 1 and so forth and so on. You know, if we could turn this into an angle like pi over 3 or 3 pi over 4 or 3 pi over 2 or something like that, I'd say this is the way to go. But the arctangent of negative 4 over 3, I'm thinking it's like negative 53 degrees or something, approximately, not exactly. And it's not something that we can turn into sines and cosines whose exact values we know. So all of a sudden, I don't think this looks like a good idea after all. So I guess I'm going to have to take an alternate approach. It was a good idea, but it's not going to work. So let's see, what do I want to do instead? I'll express Z in terms of W. And then I'll express it, and then I'll plug it in to the inequality W plus 1 minus 3I less than 5. Okay. And when I do that, if there's any justice in this world, this inequality somehow will turn into that one. So here's what I got. I have W in terms of Z. I want to rewrite this so that I get Z in terms of W, and I'm going to plug that into this son of a gun. So I guess the first thing I'll do is subtract this from both sides. And then all I have to do is divide both sides by 3 plus 4i. Or W, divide both sides by 3 minus 4i, rather. Okay, can I simplify that? I'm sure I can. W over 3 minus 4i minus 6 plus 2i over 3 plus 4i minus 4i. Oh, we got a common denominator, duh. W minus 6 minus 2i over 3 minus 4i. Okay, that's Z. And I'm going to plug it into this thing. Z is W minus 6 minus 2i all over 3 minus 4i. So that's our Z, and then we have 1 plus I. Okay. I have 3 plus 4 is 7, I hope. And I have 3i minus 4i is negative I. And I can combine numerators now because I have a common denominator. So let's see, I have w minus 6 plus 7 is 1. And minus 2i minus I is minus 3i. Okay, that looks good. I have the modulus of a quotient. And I think now may be a good time to use the fact that the modulus of a quotient is the quotient of the two moduli. So let's see, I have modulus of w plus 1 minus 3i all over modulus of 3 minus 4i less than 1. Okay. I can multiply both sides by the modulus of 3 minus 4i, and I'm going to get w plus 1 minus 3i is less than modulus of 3 minus 4i, and this is just a number. This is just a number. The modulus of this is square root of 3 squared plus negative 4 squared, which is 5. Now that may have been what we were trying to come up with. I don't remember offhand, and maybe I should check it out. Okay, this is what we were supposed to show, that the transformation from z to w transforms this disk into this disk. And son of a gun, is this really a disk? Let me rewrite it. W minus a negative 1 plus 3i less than 5. So yes, this is a disk of radius 5 and center negative 1, 3. Okay. And this thing, this is z minus negative 1 minus I. So this is a disk of radius 1. Radius 1 and center xy equals negative 1, negative I. And let's draw a picture of that transformation. -1, negative I, that's this thing, and a disk of radius 1 So here's our disk of radius 1, center -1, negative I. And here's our disk of radius 5, center -1, negative 1, positive 3. And it has, son of a gun, oh, silly me. One, two, three, four, five. So this little red disk gets transformed into that big one. And maybe there's something else I should say about this also. Oh, I apologize. I had a remark for that last exercise, and I honestly don't remember what it was I was going to say. Sorry about that. Well, let's do another one. Let's show the image of the right half plane, real part of z greater than 1, under the transformation w equals -1 plus iz minus 2 plus 3i, is the half plane v greater than u plus 7. And this is in the w plane, where v is the vertical displacement from the origin, u is the horizontal displacement from the origin. This is y, that's x in disguise. I tried this, or I started to try this in the last exercise. It didn't work. My inclination is to go with this again and try to write this transformation in the form of a rotation, a magnification, and a translation, just so we can do this geometrically. And I think it'll work. Let's see. -1 plus I convert to exponential r e to the I alpha. That's what I'm looking to do. So let's see. R equals -1 squared plus 1 squared square root. So that's square root of 2. We got the modulus. And alpha equals the arctangent of, this is 1i, so 1 over -1. And what quadrant is this in? X is negative, y is positive. That's quadrant 2. So we're going to have to add pi to this, I think. And the arctangent of -1 is negative pi over 4. Okay, so alpha equals 3 pi over 4. And -1 plus I is equal to square root of 2, that's R, times e to the I times alpha, which is 3 pi over 4. Okay. Now, what does that mean for the entire translation? W equals -1 plus I times Z minus 2 plus 3I minus 2 plus 3I. This, I just found out, is square root of 2 e to the I 3 pi over 4. That's my alpha. Now I want to rewrite this part. See, I want to write it as plus minus 2 plus 3I. Okay, so this is the translation. And this is going to equal square root of 2z e to the I 3 pi over 4 plus -2 plus 3I. That's my translation. And if I can, I'd like to do this geometrically. So I'll draw the original region, the half-plane real part of z greater than 1, and apply the rotation to it. Okay, I've drawn the original region, real part of z greater than 1. And I'm going to rotate this whole thing counterclockwise about the origin. So I guess I should label this 0, 0. But this point and this ray are going to be rotated counterclockwise, an angle of 3 pi over 4, so that this ray should end up here. This point should end up here. Three pi over 4. And notice that this line, perpendicular to the ray, this line is going to be rotated until it becomes this line. And this is our rotated region. Now let me draw that out. Just making sure I don't lose what I've got. Oh, just a minute. Oh, and let's see what we have here. This point is on the unit circle, and it's at an angle of 3 pi over 4. So the coordinates of this point are going to have to be negative square root of 2 over 2, positive square root of 2 over 2, so that's how this thing gets rotated. It would be nice if I could know what the intercepts are. The one thing I do know is that the slope of this line is 1. Oh, I just erased my formula. Shame on me. So let's see. How am I going to find either of these points? I'm going to embarrass myself if I don't pause for a second. See, I'm thinking maybe I can just use the equation of a line, because I know what the slope is, y equals mx plus b. And let's see, we know a point on the line, negative square root of 2 over 2, square root of 2 over 2. So square root of 2 over 2 equals the slope 1 times x, negative square root of 2 over 2 plus b. So I have negative square root of 2 over 2 here. I'll bring that to the other side. So I'll have square root of 2 equals b. Okay, so x equals 0, y equals square root of 2. And by symmetry, this is going to be negative square root of 2y equals 0. Okay, cool. So there's my rotation. And let's see, do I remember what this is? Oh, I hope I do. W equals square root of 2, e to the I, 3 pi over 4. Okay, I need to know what that translation is. Son of a gun. Son of a gun. Negative 2 plus 3i. I think that was it. Let me check and see if I can find it. I think that's what it was. Okay. Now, I've got my rotation. The next thing I'm going to do is my magnification. So the magnification is going to change the distances from the origin, but it's not going to change the shape any. So I'm magnifying everything by square root of 2. This point is a distance of square root of 2 from the origin. And I'm going to magnify that by square root of 2. So this now becomes negative 2, 0. This point is a distance of square root of 2 from the origin. I'm going to magnify that by square root of 2. So this point now becomes 2. And let's see. This point, should I multiply both of these by square root of 2? I think I should. In which case I'll get the point 1, 1, or negative 1, 1. Now, does that work? This point is halfway between 0 and 2, so it should be 1. This point is halfway between 0 and negative 2. It should be negative 1. So that checks out. Okay, we've done our magnification. Now we have to do a translation. So we take every point and subtract 2 from the x-coordinate, add 3 to the y-coordinate. So this will become negative 4, 3. Subtract 2 from the x-coordinate, negative 3. Add 3 to the y-coordinate, 4. Subtract 2 from the x-coordinate, add 3 to the y-coordinate. Whoops, this one is wrong. This one is wrong, 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 wrong. This should be 0, 2. There we go. Subtract 2 from the x-coordinate, negative 2. Add 3 to the y-coordinate. So that's 5, negative 2, 5. Okay, so that's the new translation. I just need to figure out where this is in terms of the x and y axes. So let's say the slope is clearly 1, and we'll let this be a point on the line. We'll use point slope form. Y minus y1 equals slope times x minus x1. So y minus 5 is equal to 1 times x minus x1, negative 2. So y minus 5 equals x plus 2, add 7. Y equals x plus 7. Okay, so 4, 5, 6, 7. I'm going to go off the board here. here's the x and y axes. Up here, this point where these two lines intersect is 0, 7. That's the y-intercept. And the x-intercept is negative 7, 0. This is the image of our transformation. And if we want to be a little bit more reasonable in how we draw it, we can scale it down to size. This is the image of the half plane, and this is the line y equals x plus 7. Let's revisit this. Show that the image of the right half plane, real part of z greater than 1, under the linear transformation w equals negative 1 plus iz minus 2 plus 3i, is the half plane v greater than u plus 7. And what we'll do, we'll solve for w in terms of z and plug that into this relationship, real part of z greater than 1. So let's see, solve for w in terms of z. Well, I guess the first thing I'm going to do is add 2 and subtract 3i. And then I guess I'll divide by negative 1 plus I. And let's see if I can just sort of write that as a complex number. So what do I do here? I'm going to multiply top and bottom by the conjugate. That's how I divide by a complex number, right? So I'll multiply top and bottom by the conjugate. And I did say conjugate, didn't I? Okay. So I have w plus 2 minus 3i. And now I have to multiply by negative I, so negative iw minus 2i, and negative I times negative 3i, that's I times 3i, which is negative 3. And on the bottom we have negative 1 squared plus, let's see, multiply by the conjugate. So we get the first thing squared minus the second thing squared. Okay. Can we tidy things up a little bit? Negative 3 plus 2 is negative 1. And negative 3i minus 2i is negative 5i. Let's see. W minus I times W, so that's 1 minus IW. 2 minus 3 is negative 1. Negative 3i minus 2i is negative 5i. And on the bottom I have 1 plus 1 is 2. Okay, let me check that. Why didn't you stop me? Let's see. Negative 1 times W is negative W. Negative 1 times 2 is negative 2. Negative 1 times 3i is plus 3i. Okay, negative I times W, negative IW, negative I times 2, negative 2i, negative I times negative I times negative 3i. Negative times negative is a positive, so this is 3i times I, which is negative 3. Good. Okay, we got the first thing squared minus the second thing squared. So that will give us 2, I hope. And I'm going to have to rewrite this because I did it all wrong. So let's see. Negative W, well, I have W times negative 1 minus I. And negative 2 minus 3 is negative 5. And 3i minus 2i is I. And now I guess I need to write W in terms of U and V, where U is the real part of W and V is the imaginary part of W. So let's see, U plus V, or IV, times negative 1 minus I minus 5 plus I over 2. And we get negative U, and negative I times I is positive 1, so we get plus V. And we get negative IV and negative IU. Minus 5 plus I. Okay. Minus U plus V minus 5. And let's see what else. Minus I times V plus U plus 1, no. Let's say plus I times minus B minus U plus 1 all over 2. Let me check that. If you see something wrong with it, speak now. If not, too late. I guess now I need to divide this into real and imaginary parts. So I have negative U plus V minus 5 over 2 plus I times negative V, negative U plus 1 over 2 . Now, where did all of this start? Where did all of this start? This is Z, and it equals this mess. So this is what I've established. Z is equal to negative U plus V minus 5 over 2 plus I times negative V, negative U plus 1 over 2 . And what were we doing here? We were solving for Z in terms of W to plug into real part of Z greater than 1. Okay, real part of Z. Here's Z, and here's the real part. Negative U plus V minus 5 over 2. And this is supposed to be greater than 1. Now, what does that tell us? Let's multiply both sides by 2, so we'll get negative U plus V minus 5 is greater than 2. And I'll add U and 5 to both sides. So V equals U plus 7. This is the V-axis, and this is the u-axis. It's a line of slope 1 and y-intercept 7. So there's the transformation of our region. I thought this way would be easier. Now I'm not quite sure. Well, I've got some homework for you. You were waiting for that, weren't you?